Today we're going to look at DeText, a deep text ranking framework with BERT. It's a work by Lincoln. It's a very interesting framework they propose, which you can plug in with like BERT language models or smaller models like CNNs. And more importantly, they experiment this framework with BERT on a lot of different search verticals on their production. And this is a very practical paper which teaches a lot of details about search ranking, which is a very important component of search engines. And in fact, this framework is just so effective and also very efficient. So they end up deploying this model, this framework with the BERT model to their production. They replace their original production search engines. And so that you can see how practical this framework is. If you are a practitioner, if you are a practical person, you are very interested in search, ranking, that kind of things, you probably won't want to miss the video today. So yeah, they perform this on 3 different search verticals. In fact, they also extend to some other tasks. So you can see there's a job search, there's a people search, there's a help center, that kind of things. And this framework is super flexible. You can plug in like CNN, LSTM models or BERT models. Yeah, so why is this paper special? Because they propose a solution that you can plug in with BERT model, and it's also very efficient to deploy to the production. And they launch it to Lincoln search engines. And also, it's a very flexible framework. If you don't really want to spend that much compute power, you can just use a easier model, which is like CNNs. And more importantly, they provide you some insights, some lessons they learn on how to deploy, how to develop the neural search engines, more specifically, ranking models. So yeah, if you would like to receive more deep learning videos like this, don't forget to subscribe, because your subscription is the best encouragement in the world for me to make more videos like this. So yes, thank you very much. Arigatou gozaimashita. There was not an accurate Japanese pronunciation. But anyway, this paper is published by Lincoln, Mountain View, California. A deep text ranking framework with BERT. So what is search? We need to talk about it first. I think most people are very familiar with search. After all, you use it every day or even every hour, right? Search is like you give a query to a search engine, and the search engine will retrieve the relevant document. Yeah, but this paper is especially focusing on ranking. So what's ranking? We need to know the relation between search and the ranking. So you can think search is like a 2-step process. We normally use a search algorithm to retrieve the relevant document candidates first. It's usually like 10,000 or 100,000 document candidates. There's still too many. And the step 2 is to use the ranking model to rank the document again by the relevancy. So at least in this paper, at least in Lincoln, they use this approach, and they didn't really reveal too much details about it. But this is what I can find from their paper. Yeah, but I believe a lot of search engines are using this similar approach. Okay, so there are 2 different types of embedding context-aware search. Context-aware means you use some deep model to calculate the representation of the text embedding of a document, instead of using traditional feature like TF-IDF. Okay, so the first I want to introduce you is the representation-based ranking. This is the most common one. Basically, it's you generate a query and the document embeddings independently. You have user query, then you use your deep context-aware deep learning model to generate a representation of text of your query. And then you also use the same model to generate the representation of a document. But the problem is usually you have maybe billions of documents. It's impossible to calculate their embeddings in the real time. So that's why people always pre-compute them and store them in the hard disk first. So we need to pre-compute the text embedding of documents. And the second step is after that you calculate the cosine similarity between the query and the document. And they select the higher the similarity score is, it should be ranked higher. By the way, here if you want to calculate in the real time, you don't need to calculate the whole document. You only need to calculate the candidates they retrieve by the first step search algorithm, but they still can be 100,000, 10,000. That's still too much to calculate in the real time. Okay, so there's some problem with representation ranking, some weaknesses. The first one is you need a lot of hard disk to store the text embedding. Like I say, you have 1 billion document, you need to store 1 billion vectors that represent those documents. That's super huge. If you have ever done this, or you ever done a smaller project to calculate text embedding and do some search, it's actually very huge. You need a lot of hard disk space to store, especially if you have a database like LinkedIn, as big as LinkedIn or even Google. That's really a tough job. And usually people use the 128 dimensional vectors around this dimension. It's quite a small dimension to represent a document. And the problem is if you use this kind of dimension to represent a document usually can contain 10,000, 100,000 words. Then how can you catch the local lexical matching? What I mean by this, for example, if people search something, the query, then they usually anticipate they can retrieve the document that really contain the words. It's like a keyword match. It's one of the requirement, right? But when you compress a document, a super long document, to this 128 dimensional vector, you hardly can catch this kind of local lexical level match, right? So that's why people usually combine this with traditional feature like a TF-IDF together to calculate the relevancy. Okay, but there are just some problems, but there are still more, pros. So that's why most production context-aware search engines, search ranking models, they are actually representation-based. As for interaction-based ranking, it's basically when you calculate the representation of document, you also need to know what a query is. One of the approach is you concatenate the query and the document together and calculate their embedding in one go. So when you calculate the representation of the document, the model also know what a query is. So depending on different query, model may pay different attention to different part of the document. So it's more like a attention mechanism, right? Depending on your query, your focus will be different. And the good thing of this is the model will pay more attention to the things that's important to their query, so that it can understand those kind of local lexical features better. That's a good thing. But the problem with that is you need to compute the document text embedding on the fly, which can be very troublesome, very slow. So that's why it's very hard to deploy in production setting. And this is 3 different search verticals. On the left is a people search. You search for people, right? And in the middle is a job search. And on the right, that's help center. So there are actually very interesting differences between them. On the left, that's people search. They actually it's not really semantic intense. Mostly it's just like a linking, entity linking. If you search some person, you just need to type match the name as name is correct, or the location maybe is also the same, or the job title is also the same, then it probably is that person. So you usually don't paraphrase in your query something. It's very simple. It's like exact match, entity linking. And on the right, the help center, there are actually a lot of paraphrasing happening. For example, maybe I want to know how do I turn on my LinkedIn chat. Then maybe the answer there's an article that's actually that contains an answer, and it says the article's title maybe is this is how you can enable your LinkedIn Messenger. So you see, I use turn on, and the article say enable, and I use LinkedIn chat, and it uses LinkedIn Messenger. A lot of these kind of things happening in help center. So that's where the paraphrasing is being used a lot, and that's also the area where deep contextual models are good at. So you can foresee that the BERT model probably can perform quite well in this vertical. And here is their framework. They propose this deep text framework. There are 5 layers of the framework. The first one is very simple. It's token embedding. You can use if you use LSTM, CNNs, then you probably want to use the glove or watervect as your pre-calculate word embedding. But if you use BERT, that is just naturally contain the first layer is the token embedding layer. Okay, so another is text embedding layer, right? If it's BERT, it's just these 2 chunks, just the same. But if it's a text embedding layer, when you are using CNN, LSTM, it's just the main model is CNN here, CNNs and LSTMs. How many layers you can use depending on how sophisticated you want your model to be. And also after that, they have the interaction layer. It's the layer that allows you to combine with the traditional feature. But don't get confused. The interaction layer here, they have the interaction layer here. Doesn't mean it is interaction based. It's still the presentation based ranking, because when you calculate the document embeddings, you don't know the query, right? So you pre-calculate them. And after that, you have one multi-layer perception. Basically, you combine the deep features they calculate from text embeddings by the BERT model or some other deep learning models. You combine with the traditional features. Then you fit into the multi-layer perceptron. They calculate the score. And the last layer is learning to rank layer. Yeah. Which is very interesting. And one thing worth noting is they don't just put the traditional features and calculate that. They do some processing. That's extremely important. If you don't do that, your model will not perform well, which I'll cover later. So let's go through the interaction layer a little bit. But basically, you calculate the embedding of a document and also of a query. Then you want to calculate how similar this document and the queries are. There are a few ways to do that. The straightforward way, most straightforward way, is cosine similarity. You do a cosine similarity, which is like this. Then you will have one feature, which is a scalar from 0 to 1. The higher means they are the more similar. And another one is a Hindenburg product. If you don't understand what Hindenburg product is, it's basically very simple. You have 2 matrices, then their operation is like this. You use the matrix element 1 1, basically do the multiplication to the matrix element B1 1, and so on. So it's very straightforward. And let's say if you have D feature for one document, then you will still, after the Hindenburg product, you will still have D feature for the similarity. And another one is do the concatenation. Basically, is to concatenate these two vectors. So there are three ways, and you can choose whatever you want. But after they have done a lot of experiments, they found out concise similarity and the Handmer products are most effective ones. So they basically use these two for their production. And here is the more important one is a traditional feature processing. So how to process those traditional features? Let's just take a look at what the traditional features are. Those features are similar like the personalization or social networks. Is basically you handcraft it. They have a social network in LinkedIn, and basically it's a graph. Then you do some handcraft features to extract certain property of the network, and also you also have the behavioral features of users. Those are very like handcrafted features, but you cannot just fit in because they have different scale and the distribution. Then the first process is to use the mean and the standard deviation to do some normalization work, but that's not enough. They also put another feed-forward neural network. Basically, you put in your input as this process, normalized traditional feature, and you have one feed-forward neural network. You have the matrix W and the bias term B. These two parameters are learned. Parameters are learned, yes. And you have the process feature, which is more effective. And the last layer is learning to rank layer. So learning to rank is kind of a very popular algorithm or methodology that people use to improve their search algorithms, search engines. The easiest one is point-wise learning to rank. Basically, it's a loss function. It's binary loss function, binary classification. If this document is clicked, and they say you will have a lot of document candidates, maybe 10, then only 2 of them got clicked. Then 2 of them, the 2 they got clicked, they're in the binary classification term is true, and the rest are false. So basically, you do 10. In this case, you have 10 binary classification. And for the pairwise and the listwise, it's slightly more complex. It's like for pairwise, you consider 2 documents at once, and the listwise, you consider a lot of documents at once. It's like in my example, there are 10 documents, so you consider those 10 documents at once into your loss function. And in reality, that's non-trivial in terms of implementation, and there's also a lot more details than what I just mentioned. So if you're interested in that, look it up on Google. You search learning to rank algorithm, then you can see those differences. But this is not the main focus in this video. And as for the DeText-BERT for ranking, as I said, their framework allow you to use BERT. BERT is like one component in their framework. But the tricky part is if you use the same learning rate for multi-layer perceptron and some other layers, simple neural network there, and also uses the same optimizer for BERT, then you will not have good result. So they have 2 different learning rates. One is for BERT, which is quite small, and another is larger learning rate for the rest of neural network. And this is one tricky part, very important. And also they fine-tune this BERT, the whole network on the click-through data. Is like, let's say we retrieve 10 documents, then you fine-tune that on the click-through rate, which document got clicked, right? Just like I say, the learning to rank is a final layer. It's a final layer to calculate those. So that's why you need click-through data. And also, more importantly, if you use the standard BERT, like a pre-trained BERT, they train on the Wikipedia, Google Books, corpus, then you basically will not have that much performance. Why? Because in the linking context, there are so many company names, which is OOV, out of vocabulary in the general BERT, pre-trained BERT, general pre-trained BERT. For example, Pinterest and LinkedIn, it's now a vocabulary in the off-the-shelf BERT. So that's why they pre-train their own BERT on linking data, and they also use the smaller number of parameters. Basically, if I'm not wrong, it's a 6-layer BERT, and also fewer attention heads to pre-train this BERT, and they retrieve basically the better result in the larger BERT, while they only use 1/3 of the parameters of the BERT-based model. Yeah, so here's the data they use to train their linking BERT. The tricky part is in the linking data, it's like semi-structure. You don't have like Wikipedia, one document and the free form of text over maybe some table, but most of like free form text. You don't have that. In linking, you have search queries, member profiles, and profile also can be, broken down as member headlines and member position titles and descriptions. Those kind of are not really continuous text. So how to deal with that? There must be a lot of pre-processing being done. And also job post, you have job title, job description, also help centers query and document title. This is the data they fit into their linking BERT they use for pre-training. And how many words are here, they already give you a hint. So this is like, if you are also wanting to train something like this in your domain, then you can consider this way of feeding data, because it's definitely very different from research, the pure research. We can train on Wikipedia, Google Books, corpus without thinking too much about it. But in the industrial usage, we usually need to consider a lot how to feed the data. That will be the difference in terms of performance. And here is the document embedding pre-computing. Basically, you store your pre-compute document embeddings here. Those embeddings are generated by BERT. Then, like I say, there are two-step process. The first one is to user input a query, then you use your search engine to retrieve relevant candidate. No, it's not like it's document candidates. As for how this part work, he actually did not explain in the paper, but you can look up more research. And after you have the document candidates, you use the document ID to retrieve the corresponding document embeddings. So you have those document embeddings for those document candidates. Then you perform the ranking part of, basically you use the DeText model, just like what I mentioned previously. Then you rank the model. Yeah, this is how it works. As for the CNN, because you also can use CNN as your embedding generator, right? But the problem is, even the candidate, the first stage, they usually retrieve 100,000 candidates, but that's still too much for CNN to calculate on the fly. Because for CNN, they actually calculate on the fly, but that's 100,000. That's too many to calculate on the fly. And what I did was they used like two-step ranking. The first is they use a multi-layer perceptron to retrieve 100 relevant, very, very relevant documents. It's very simple. They use probably traditional features then to retrieve 100 plus documents. And this is a step to filter out those irrelevant documents. And then the second stage is to use the DeText-CNN to calculate. The CNN is basically so one-dimensional CNN to like scan through the word, and they have like different window size, different filters. Then you can retrieve the more relevant results here. Then later I will compare the performance between CNN model and the BERT model. And this is their experiment setup. They have the matrix like they don't actually show the absolute accuracy, F1 score, that kind of thing, due to the business reasons. They just cannot reveal that much. So they only show us the relative improvement, how many percentage it improved compared to their baseline models. And their baseline models are XGBoost for ranking. So it's basically their production setting. Before this paper, I think until recent maybe month or 2 months, they used XGBoost to rank the linking document. Remember this graph? This is their framework and their end-to-end model. Then we just talk about the structure of CNN and the BERT model, how they pre-train BERT, but we didn't really talk about what are the training data sets they should be used to train this model. So in that experiment, they selected the training data from 2 months online traffic, which is 5 million people search, 1.5 million job search, and 340,000 help center search. So it's very interesting. You can see on the LinkedIn, people search for people most. Then the second is job search, right? So there's 2 months traffic. And you also know 2 months traffic is like this. And for the development data set and the test data set, test data set, they select 50,000 query for each verticals from the later month. So that's how they evaluate things. And they have offline experiments and also online experiments. Offline experiments basically run it offline. So you can run it longer, but for online experiments, it's more tricky. You need to be fast enough. And also when you do an online experiment, you basically select at least partial their user base to do the experiment. So your models cannot suck in that case, because it's really the real users are using that. So let's look at the offline model first. Offline experiments, the first experiment, they want to know how good is DeText framework. So they compare the DeText. Basically, it's also DeText, but it's a DeText with only multi-layer perception. Basically, you just use the traditional features without using deep learning generated embeddings. So it's not really like DeText, but they just fit into this framework and as a baseline. And second model is CNN model, DeText-CNN model, and DeText plus linking BERT, LinBERT. So you can see in the people search, these two deep learning models improve the results, but it's not that much. And in the help center, just like I say, there are a lot of paraphrasing. So deep learning models are really good at recognizing paraphrasing because you understand the deeper semantic, syntactic things. So he basically knows paraphrasing better. So the performance improve like 10%, 11%, 13%. It's really huge. It's really huge. But with this metric is normalized DCG is a way that people usually use to evaluate the search result. If you are not familiar with this, look it up on Google. There are some explanation there. And also for the job search is like in the middle. It's partially entity linking, but it's not exactly that. It's still they contain like free text. Imagine your job profile, you have job search, it's not, the company job description has like some natural languages in there, but people search is more like just the linking entity, right? So that's the improvement. And if you compare the CNN model with the BERT model, you can see the difference in the help centers is larger because it requires more semantic and syntactic language abilities. And BERT model definitely is better at that. And the job search also improved like 1.5%, which is probably significant. But in the people search, you cannot tell too much difference. And second experiment is they want to know in-domain BERT. How does the in-domain BERT compare to a general BERT? In-domain BERT is basically the BERT trained on the linking data. So in the people search, it's not much different because it's just the semantic level understanding is not important. But for the job search in the help center search, it's quite significant. And for some reason, the job search, the kind of linking BERT has a much better performance than general BERT. Why? That's actually a very simple reason. Because there are a lot of out of vocabulary in the job search. You use either like company names, like technologies, terminology, those kind of things. Like general BERT probably like doesn't contain that. But if you really pre-train the BERT on the linking data, you will know that. You will be included in its vocabulary. Yeah, so it improved like 2.5%. Quite a lot. I would say quite a lot. So even if you use the BERT-based model, your accuracy just will be lower than CNN because CNN is probably trained from scratch, right? No, not really sure. It's maybe they add a new vocabulary. Not sure how they train, but get the idea. The idea is if you pre-train the BERT on the in-domain data, then your performance is so much better in this case. It will also happen in other cases like a biomedical domain. There are a lot of chemical compound, drug names, that kind of things. So in that kind of case, pre-training on the in-domain data is super important. Okay, so you know how the limber is performed, and also limber also only uses 1/3 of parameters compared to BERT-based model. So that's even more impressive because your speed is much faster and memory usage is much less, but you still can outperform the BERT-based model quite a lot, right? Okay, so they also do some ablation test on the traditional feature. And so first line they don't use traditional feature at all, and this is like a DeText-CNN model, and it's a baseline, right? So you can see like performance like decrease a lot, and those compared to the baseline model, real baseline model, the XGBoost, right? And the interesting thing is, even you don't use traditional feature in the help center category, it improves a lot. So this just tells us in the help center, this is kind of semantic heavy search vertical. Traditional feature is just not important, but in this like people job search, like those kind of requires linking, entity linking, then traditional features should become very important. Okay, so they also do a rescale and also normalization to the traditional feature, and the result is when you do a rescale and the normalization together, your result will be the best. Oh yeah, so as for very exciting online experiments, they introduce several metrics that we need to know. So the first one is click-through rate, top five click-through rate. Basically, it's a way to measure how many searchers they got clicked in the first top 5 items in the search result. For example, if I search something, then if I search deep learning explainer, then there will be a list of results, right? Relevant documents. And if the result that I end up clicked is in the top 5 items, then you will be considered true. Then if I didn't click or I click the other than top 5 item, you'll be considered false, which is incorrect. Okay, so another one is session success rate. It's basically to make sure if the user is satisfied in one search session. So how they measure is if user did not search the same thing, similar things in 30 minutes in the help center, then you consider the session search is success. This is especially for help center. And another one is for job application. For this one, is number of job the user apply from a search, right? So if this is very relevant search, the user should apply a lot of jobs. Okay. Another one is happy path rate. It's basically to make sure how happy the customer is. So if the customer search in the help center, then they did not use the help center in the next day. In that day. They said today I used the help center, then I did not use the help center today, and did not create a ticket something. Then you will consider the happy pass rate. It's very domain specific, but anyway, it's some metrics that we need to know. And this is their online experiment. This experiment is meant to compare the DeText-CNN and DeText-BERT. And we can see in the people search, they are not much different. I would say it's pretty much similar performance because people search will require less semantic understanding. For the job search, you can see they didn't have the result for BERT because the cost is too high. So they did not perform the experiment. They only run a CNN. Also, still like a top 5 click-through rate is still 3% over the baseline, which is quite significant. And for the help center, it's most interesting because you can see the CNN model and the BERT model both have very, very strong performance improvement over the baseline model. You can see the customer happy path rate is improved 15%. And for the BERT model, DeText-BERT model, this happy path rate increased 26%, which is insane. And for the session success rate, also very significant, especially for the BERT, it improved over 11%. And so this is just a proof for how effective the DeText framework is. Also the BERT model, and also pre-trained on in domain data's BERT model. And also when you deploy the search engine online, the one thing you care most is latency. And what is the most important metric for measuring latency is latency at 99 percentile. Basically is to find out the 1% of the search there's 1% slowest search. So they care like the search cannot be too slow. Even maybe on average the search is very fast, but as long as they are certain percentage of searches are very slow, then it's considered fail. So that's why they always look at the 99 percentile latency. So in this data, you can see the CNN, if you do the all decoding, basically, like I mentioned previously, there are 2-pass ranking. If they don't do 2-pass ranking, they just rank the whole document, then the latency is like 55 milliseconds plus compared to the baseline, basically. And also if you do the 2-pass ranking, then it's like only 21% milliseconds more than the baseline, which is quite good, very good actually. Consider CNN is much complex model compared to the baseline, right? And for BERT, BERT is much smaller than the BERT-based model, and you can see from the speed is like much different, right? So BERT is really good because it's faster and more accurate. Okay, so what did we learn today? We learned that BERT is very strong at handling paraphrasing, like help center search. So if your product, if it's something you want to build it's related to like very semantic heavy search, then you may consider using BERT or other transformer based model to your search engine to improve them. And also the domain adaptation is very important. Yeah, if you are doing something that's very like your domain is very different from the general domains like news, Wikipedia, that kind of thing, you may consider pre-train your in-domain data, right? And that's second lesson. And the last one, what we learned is basically is a bonus. They open source this, and there are a lot of people using. If you look at the GitHub, it's like a lot of stars already. So it's a very popular framework, a ranking framework. So if you want to try it, don't hesitate to play around. It will be very interesting and very, I think, a lot of things to learn from this framework, right? So yeah, this is the end of this video. And if you are very interested in search, which I believe you do because you like watch until this very end, right? I have other video which is this open domain question answering state-of-the-art model they proposed by Google AI, and I will put a link in the description down below so you can check it out. And that's kind of a knowledge retrieval model, very interesting as well. And other than that, if you would like to receive more deep learning videos like this, don't forget to subscribe. Your subscription is really the best encouragement for me to make more videos like this. Yeah, and other than that, I will see you in the next video, and take care.